Hey, this is chapter 31. It's about another type of welding processes. It's called as solid state welding processes. The main difference with respect to previous welding processes is that we don't have any phase change. We are not changing, we are not using any liquid or semi-liquid kind of material or some part of the material in this welding processes. And we will be actually discussing such type of welding process in this chapter. And we can talk about briefly about some basic issues regarding these type of welding processes first. First of all, we don't use any filler metal in this process, so we should be bringing these interfaces parts which are to be actually joined together very close to each other, and then by using some means, by using pressure, by using some little heats, generate internally or externally, with the help of it to try to join the parts together. And the thing is that the surfaces should be quite cleaner, otherwise we'll have difficulties and the strength of the bond will be less. So what kind of things actually we have in solid state bonding? We may make use of heat, pressure, and some relative interfacial movements. And you may have one of them or two or three of them at the same time. It's up to the type of process you are using. And let's talk about the heat. With the help of the heat, actually, once you increase the temperature by simply applying heat, the diffusion will be increased and atoms will be actually transferred between each other, and the quality, the strength of the bond will be improved. And for heat generation, we may use internal heat generation like friction, or we may use electrical resistances so that while the currents are flowing, they may increase the temperature. Or lastly, we can have external heating like using inductions. But for most of the time, we use internal and through electrical resistance heating. Considering the pressure, since the parts are usually in contact with each other, if you increase the pressure, then you have more plastic deformation, and again, the strength of the bond will be improved. And lastly, we may have some interfacial movements, so that with the help of actually this movements, we will have some connections, we will have more plastic deformation again, and the parts will be bonded easily. And while having actually interfacial movements, we are also cleaning the surfaces, so with the help of them again, the strength of the bond, the weld will be improved. Now let's talk about the first type of solid state bonding process. It's a very simple process called cold welding, and we have a variation of it called as roll bonding. And in this one, as the name implies, we don't have any heating equipment. We are not heating. We don't generate heat internally or externally. What we do, we simply apply pressure. So in this one, we are only using pressure, and we can apply this pressure through the help of dies or through the help of rollers. And the thing is that since while you're applying pressure, we make use of plastic deformation, and that might not be actually achieved if the parts are quite brittle. So this process is not applied on the brittle materials, but if the material has some sufficient ductility, then that is possible. By applying some force pressure on the parts, we can join them together. So that's why we mostly prefer it for non-ferrous metals. We don't use it with some steel or kind of things, since we want to have higher ductility. And on the other hand, the similarity of the materials are highly important for it. If you want to try to join aluminum and steel together, then that will be quite, you will have a quite weaker joint, weaker bone, and since they are not similar, so when somebody, it's better we use some similar materials. With the help of this, we can increase the strength between the parts. And we have a version of this, a variation of this one called roll bonding. As the name implies, we are using rolls. What we do, we have base metal, and if you want to do some coating on the base metal, you place your materials on top and bottom. It's up to you. You may only have top part, but what you then, you feed all these into the gap between the rolls, and with the help of the pressure they are applying, and they also feed this material through the nozzle, and that is a quite simpler process, and we use it mostly for the manufacturing of coins or manufacturing of some bimetallic strips. So in bimetallic strips, we have usually different materials having different mechanical properties, like different thermal expansion, and they are joined together with the help of this simple process. Another example might be joining such kind of actually pipes onto the sheet metals. This is highly utilized in the manufacturing of actually refrigerator evaporators. Now we have another type of solid state welding process. It's called as ultrasonic welding, and it's somehow similar to ultrasonic machining. We are using similar equipment, but we don't have any obviously abrasive particles in between. This time our aim is to join the parts together, and we again have obviously high frequency oscillations at the tip of our tool, and this time we have a normal force, which is actually constant, it's not vibrating, and we have actually horizontal vibratory motions. And let me show you the schematic of it. This is our transducer with the help of electrical currents applied here. We have vibration, low amplitude, high frequency vibration, and you see this normal force is applied, and the materials underneath actually is with the help of this interfacial movement, they are joined together. So in this one, we are making use of the third actually approach of solid state welding processes. So with the help of this shearing process, shearing stresses, we generate plastic deformation. With the help of it, the surfaces are cleaned and they are bonded together. And the strength of the bond is quite high, but the equipment is expensive. So it's up to you. You should consider your requirements and then decide whether this one is a nice approach for your company or not. Now you'll discuss another group of welding processes. These are called as friction welding, and in these we are using heat generated by the internal ways. Actually, we make use of friction. With the help of the friction, heat is generated, and the interface actually will be in a semi-solid state, and then by applying some little forces, the parts will be joined together. And the most popular type is actually using such cylindrical parts, circular products. This is a nice example of friction welding. So what we do, one part of this welding is actually stationary and the other part is rotating at very high speeds, and then we apply force. So once you decrease the gap between them, what will happen? We will have friction since we have a relative movement between the parts. So we will have friction at this interface, heat will be generated, and the temperature of this region will be increased. And we continue increasing the pressure. And once you do that, like in the case of actually some other type of welding process we discussed by using oxy-fuel pressure gas welding, the principles are somehow similar, but this time we don't use any torch. We make use of the friction so that heat is generated and the temperature of this part is increased. So once we apply pressure, we will have some extra material around this interface, and then later, once it's actually we suddenly stop this part, so that right now there is no relative movement, but we continue applying the pressure so that the bond is having quite good strength, and then the process will be completed. Obviously, at the end of the process, we can simply do trimming, machining, so that flash is removed. This figure, this plot is quite nice, actually showing the change of speed, force, and offset length during time. Let's have a look at speed. At the first process, at the first stage, we are increasing the speed of our rotating part. And then what we do, we close them, we close the gap, and we generate actually heat due to the friction, but the speed of the part is the same. It's at a constant level. And then in the third stage, we actually start decreasing the speed of this part, the left part, but continue applying the force. And then in the fourth stage, actually, you see we have zero speed. That means this part is stopped, but we continue applying force. Now let's have a look at the force. Obviously, once you have a gap, we don't have any force in between the parts. But in the second stage, as you see, we have a constant force. And then once actually this part is stopped, we increase this force, the amount of the force, so that the part is actually going to be welded in a stronger way. And we kept this pressure at a constant level for some time, and then release the force. So once it's done, actually, then you can go with some extra machining operations and have your welds finished. And we mostly use this one for rotational, axis symmetrical parts actually. If you have complicated parts, then that will be quite complicated actually to use friction welding. So that's mostly preferred on rotational, on parts having rotational symmetry. And we also make use of different materials. We don't have much limitation, provided that left and right parts have similar behaviors. They can be joined together. We have another version of it. This is called as inertia friction welding. The difference with respect to the previous one is that we don't use helical motors this time. The rotational speed is provided by a large flywheel, but the rest is the same. Then we have the linear friction welding version. The idea is the same, but this time the part is not rotating. The part is actually moving in the horizontal axis at very high speeds. And again, due to the force and this relative motion, we generate heat and we can join the parts together. Then we have friction stir welding. This is quite popular these days. It's a quite new process, new friction welding process compared to the other ones. And it has nice advantages, especially in terms of aluminum welding. Some of you were asking in the previous lectures about how to join aluminum parts, how to weld aluminum parts. It's quite difficult, but these days there are some companies in Ankara even. We have about 5 to 10 companies working on friction stir welding. And in this welding process, the parts are actually quite stationary, but the probe actually, which is moving at the interface, moving in between the parts, is rotating, and this is non-consumable. Yeah, that is the part. These are the parts, as you see, and they are stationary, they are not moving. We put them beside each other, and then what we do, we have this hat, and at the tip of this hat, we have a non-consumable rotating probe. And it's usually made of CBN, cubic boron nitride. It has high hardness, and then it goes into this interface, kind of stirs this interface so that we have atoms actually moving in between the parts. We have a kind of a weld in between the parts. That is a nice and a neat way of joining the parts together. And there are aerospace, automotive, shipbuilding companies using this technology. And this one has actually less limitation, and you can even actually use this welding process on thinner and thicker workpieces. And this process actually have usually high quality. We don't have much porosity inside the weld, and the material properties are quite uniform. So that's why these companies are switching to friction stir welding in some critical products. Now let's talk about another main group of solid state welding process. This is resistance welding. And as the name implies, this time we will be generating heat with the help of actually electrical resistance. So current will be flowing in between the products and the probes. And due to the resistance of them, we will be generating heat, and that will be we will be using it for the welding process. And as opposed to the other actually arc welding processes, we are not consuming the electrodes. We are not using any shielding gas, any flux, so that's much simpler. It is quicker than the other process, and it's highly suitable for automation. So at the tip of your actually robotic manipulators, you can have such end effectors, and they can perform welding operation. So if you remember, we said that gas metal arc welding is highly suitable for automation, and this is another one, another welding process which is highly suitable for automating these welding processes. And in this process, we generate heat, and heat depends, as you see, on the current flowing, the resistance of the items, and the time you are applying this current. And during this welding operation, obviously, some of the heat will be lost as conduction and radiation. So that's why, in addition to this equation, we have a parameter called K, and obviously that should be less than unity, so that if you, depending on the type of electrode, the type of materials you are using, that K value may change. And if you do the simple multiplication, you can obtain the heat generated. We can say that if you increase the current or if you increase the resistance of the items, then we will be generating more heat. So let's have a look at the fundamentals of this process, how we do it. So these blue ones are actually the parts we want to join together. And these gray ones are the electrodes. You see upper electrode and lower electrode. They are made of same material. And now what we do, once we apply force, a little pressure, we turn on the current, and then current will be flowing from one of the electrodes to the other one. And while the currents are moving, we will be generating heat, since we have resistance between the electrodes, between the workpiece, between the interface. Due to the resistances, we are generating heat. And as you know, with the help of heat, the temperatures will be increased, and we will be actually easing the diffusion process, and we will have a kind of an solid state bond between the products. And this weld zone is called simply as weld nugget. And after this is actually obtained, we simply release the force and get our joined products. And the resistance here actually depends on the resistance of the electrodes. Obviously, the resistance between the electrode and the workpiece, we have one here and one here, other interface. And also we have the resistances of the parts, the resistance of this lower part, upper part, and we have further resistance in between at the interface between these blue parts. So the summation of these resistances give us the total resistance in this welding process. And these days, actually, we can easily make use of some CNC type of machines to perform this welding process. As I mentioned, we can further use robots. It's not a complicated thing. This is a typical, let's say, end effector. If you can somehow mount this end effector to your robot, then you can join any kind of sheet metals together. So it's mostly suitable for joining sheet metals. Now we'll be talking about some types of resistance welding. The first one is the simplest one, and we have a kind of an example equipment in our machine shop. This is resistance spot welding. Not complicated. We are following the main principles of resistance welding. So if you have just a single dot, let me show you here. So if you simply join the parts from a single point, then it is simply called as actually resistance spot welding, or RSW. Now we'll be seeing that there are different variations of it. If you use actually sequence of these dots after each other, then it's called as resistance seam welding. So you are kind of actually drawing a line, and for that purpose, we use actually a kind of electrodes in the form of wheels. You see, this is these are the two parts to be joined together. That is the interface, and we are feeding this interface in between the electrodes. And while it's moving, we also actually transfer current from this upper electrode to the lower one. With the help of them, we generate little spots, and that's why it's called as simply seam welding. And depending on actually the, let's say, frequency of your currents, you may have gaps in between the nuggets, or you may not have some gaps. That is a kind of an overlapping. Obviously, the strength of this one is better. So depending on your overall requirements, you may increase the frequency of your currents, or you may decrease the current flowing through this electrodes. And then we have another version of this one, another version of resistance seam welding. This is called as high frequency resistance welding. Obviously, the difference is that the frequency of current is much higher. That is mostly utilized for thicker ones or some kind of tubes having higher thicknesses. As you see, this is an high frequency continuous butt welding, but the ideas are the same. The fundamentals are the same. Then we have resistance projection welding, and this is a very nice process for complicated products. If you have many regions to be actually welded, then you may consider using resistance projection welding. Let me talk about over this schematic. Here you see we have two parts to be joined together, but if you look at it carefully, we have some projections. There are two projections, so if we apply current, what will happen? Current first will be flowing through these two projections. So heat will be generated at these regions, and these parts will be welded, but not the other regions. So that's a nice feature. You can simply form some projections and then apply your current, and you'll actually be joining the parts only from these projections. So that's a nice property. You see, we have another example here. This is a nut, and we have a kind of a cap, and we have projections here, one projection, another projection. So once we apply current with ladle force, we will only have two weld nuggets at this region. Another example, this is a very nice one. So you place many bars on top of each other, and if you apply currents, what will happen? It will be flowing only through this actually contacting points. So with the help of it, we can, in some seconds, we can join the parts together by using the fundamentals of resistance projection welding. Then we have flash welding. This is, again, in this one, we are using electrical arc, electrical current, and this is very similar to actually pressure gas welding. If you remember it from the previous chapter, we were using a torch, heating the interface, and then applying pressure, and we were generating flash. Right now, we will also do the same, but the difference is that instead of using an extra external heater, what we will do, we will apply current through these actually parts, and with the help of the current, we will be generating heat, and the interface again will be heated, and with little pressure, we will have some diffusion, and the parts will be joined together. And we have some critical design guidelines for this type of flash welding. It's better you have same thickness, actually same cross section at the interface. For instance, this is called as pure sense. This one is actually a quite larger product, and the other one is a bit smaller. So that will be quite difficult to obtain or generate proper heat in between. Or in another case, this is a kind of a tube shape. So if it's a tube, then the other part should be also in the form of a tube. That will be quite difficult if the left part is kind of a solid, but the other one is tube. So these are main guidelines for this process. Now we have another arc type of actually electrical resistance type of welding process. This is called stud welding. And in the stud welding, we are usually trying to actually weld some screws, bolts, nuts, fasteners onto the flat surfaces. And I will show you a kind of a video about this process in the lectures. During the lectures, they have a gun, and with the help of this gun, they simply push this stud or screw to the surface, and then we will be actually transferring current from the stud to the workpiece, and then later in some milliseconds we actually pull back our stud so that we will be generating arcs. Since if you don't have any gap, no arcs will be generated, but if you have little gap in between, then arcs will be generated, and we will be melting this little part, and the parts will be joined together with an extra pushing action. Actually, with the help of it, this part is actually pushed into the molten zone, and this stud is welded to the sheet metal. And it's obviously highly similar to flash welding. but the type of arc generation is a bit different. Then we have percussion welding. It's very similar, but this time instead of a constant actually power supply, we make use of a capacitor, and this energy is supplied from the capacitor, and we can discharge actually this energy in 1 or 10 milliseconds. Is highly suitable for if you don't want to actually harm the other regions in your assembly. If you want to focus this energy onto a specific point, then that is highly suitable. In such cases, we should be using percussion welding. Now we have another type of solid state welding process. This is explosion welding. It's very similar to explosive forming, if you remember in our forming chapters. What we use obviously kind of an explosive, and then with the help of this detonator, we spark it, we generate this, we start the reaction, and then with the help of these impact forces, this blue part is actually clad metal, is pushed onto the surface, onto the base plate, and then with the help of the impact forces and the pressure we are applying in this explosive operation, we have good bonds between the products. And the advantage is that we can easily apply it on very large products. We can clad such larger plates on top of each other. Then we have diffusion bonding, and in the diffusion bonding, obviously, the primary joint actually forms due to the diffusion. And in this primary operation, the atoms are actually moving in between the products, so at the interface. And the secondary joining is actually plastic deformation. So we have less plastic deformation, but more diffusion. We have more atoms moving at the interface. And for that purpose, actually, if you want to increase the amount of diffusion, then we need to be increasing the temperature to a bit higher levels to usually half of the melting point. And if you do that, then you can have a better diffusion between the product. And that is simply mostly utilized for dissimilar metals. If you remember our previous discussion, we said that we prefer to join similar materials together with other welding process. But for diffusion bonding, that is not the case. We can easily join some dissimilar metals. And if you remember, we were also using this bonding process in our powder metallurgy manufacturing process, that we were sintering the powders together, and there were different types of sintering mechanisms, and one of them was diffusion bonding. But the thing is that this is obviously quite slower, since the parts should be at the temperatures of their 0.5 of their melting point temperatures. If you want to reach to that levels, you need to apply more heat and wait for some time. And that is actually all for this chapter, guys. Please make sure that you have a look at the questions here while studying for the quiz and for the final examination.